How does system stability analysis balance performance and instability? Imagine trying to make a car go faster without losing control. That's similar to what engineers do when they analyze system stability. They want systems to perform well but not tip into instability. In electrical engineering, especially in control systems and signal processing, this balancing act is vital. Stability analysis helps determine if a system will stay steady or start oscillating wildly. It involves studying how the system responds to different inputs and disturbances. The key is to keep the system responsive but not so aggressive that it becomes unstable. To do this, engineers look at the characteristic equation of the system, which comes from the control system's transfer function. For systems that don't change over time, called linear time-invariant systems, stability depends on where the poles of this equation are located in the complex plane. If all poles are in the left half of the plane, the system is stable. Poles on or near the imaginary axis can cause oscillations or marginal stability, while poles on the right side lead to outputs that grow without bound. One common method to check stability is the Routh-Hurwitz criterion. It uses the coefficients of the characteristic polynomial to quickly tell if the system is stable. If all the elements in the first column of the Routh array are positive, the system is stable. Engineers can then tweak parameters like gain to keep the poles in the safe zone, balancing speed and stability. Another useful tool is the root-locus method. It shows how the poles move in the complex plane as a system parameter, often gain, changes. By observing the root locus, engineers can see how increasing gain makes the system respond faster but also risks pushing poles into the unstable right half-plane. This visualization helps find the sweet spot where the system responds quickly but stays stable. Frequency response analysis, called the Nyquist stability criterion, looks at how the system reacts to different frequencies. It plots the open-loop transfer function and checks how it encircles a critical point in the complex plane. This method helps determine how much margin there is before the system becomes unstable, especially when parameters change or disturbances occur. Eigenvalue analysis is another approach used mainly for multivariable systems. It involves calculating the eigenvalues of the system matrix. If all eigenvalues have negative real parts, the system will settle down over time. This method is especially helpful for modern control systems that have many inputs and outputs. Balancing performance and instability means adjusting system parameters so the poles stay far enough to the left for quick, stable responses. But if the poles are too far left, it might requiring excessive control effort or make the system overly sensitive to noise. For example, increasing gain can improve response speed but might also cause oscillations if it pushes poles too close to the imaginary axis. In real-world electrical engineering, stability analysis guides the design of controllers for power grids, communication systems, and signal filters. It ensures these systems respond swiftly to changes or disturbances without oscillating or breaking down. By understanding where the poles are and how they move, engineers can set the right parameters to keep systems both fast and stable. So, in essence, system stability analysis acts like a balancing act. It helps engineers choose the right settings so that systems perform well, respond quickly, and stay steady over time. This careful tuning is what makes reliable, efficient electrical control systems possible.